So a recursive definition is composed of two parts, the basis step and then the recursive step. So the basis will specify the value of the function at 0 or at 1 if 0 is not possible. Then the recursive step will give the rule for finding its value at an integer from its values at smaller integers. Or to put it simply, in the recursive step, you're going to express the next term in terms of the previous terms. So for example, we have a recursive definition. f0 is 3, and you have f of n plus 1, the next term, is equals to twice of fn, the previous, plus 3. Or somehow we could write this as the current term. So this is the current term, f of n, and we could say that is twice of the previous plus 3. So whichever the case, they're both valid as a recursive step. So you could try to code them, and if we recall first one, so the first one is f of 0 is 3. So if you code them, basically I'm just going to write a function f, and let's limit to integers for now. So int f, and let me just accept an integer, say n, and this algorithm is basically an if-else statement. So if n is 0, then you are going to return 3. Else you're going to return the twice of the previous plus 3. The twice of the previous, which is f of n minus 1, and that's the parenthesis area is not required because multiplication is higher precedence than addition. So plus 3, and that's it. So we have now twice of fn minus 1 plus 3. So we could test this by printing f1, f2, f3, and f4. So let's try to print f. What is, say, f of 1 is equals to f of 1. And we could just copy paste this for f2, f3, and f4. So I have F1, I have 2, 3, and 4. So I have 2, 3, 4. Okay, so let's try to run this. Okay, so now we have the result, which is 9, 21, 45, and 93. So the way this works is basically you have the program will enter the main, and then we'll go to your function call f, and then after that it will go to your definition f, and for example if f is equals to 1, it's not 0, so it will go to the else, and then if we'll compute f of 1 minus 1, which is 0, and it will go to the function again. So if it is 0, then it will return I made a mistake, so this is not 3, return 1. So that is return 3. I just mistake it for something else. So if it is 0, it will return 3, and when this is 3, it will become 3 times 2, 6, plus 3, which will be equals to 9. So that's the case when it is 1. For the other case, when it is 2, it will be a different story. So when it is 2, so it's coming from the first line. When it becomes f of 2, it will again go to the definition. It will make this n equals 0 will be false, so it will go to the else. So this is twice of f2 minus 1, so this will be f of 1. But we don't know f of 1, so it will go back to its definition. And we'll ask again, is 1 equals to 0? So if it's not, then it will go again to the else. And then it will become 1 minus 1, so twice of f0. So in that case, it will give an f0, so that is, which is going to the definition again, it will give you 3. And then when you go back with 3, you will get a 2 times 3 plus 3, which will become 9. And when it becomes 9, it will be substituted to f of 1, so 9 times 2 will become 18 plus 3 will become 21. So, and then the 21 will be returned here to the calling function. So calling code 21. So that's why when we run it, we had 21 as the second element. So basically that's it for the solution of this exercise.